So as usual, so here's the Slido code for polls, etc. You just go to this website and put the code. I'll leave the code here. Just a reminder that you can find all the lecture notes and the recordings on the website. And as well, for the people who are joining from YouTube, I used to send you the link each time. Now you can just find it on the website a few hours before the lecture. I put the link for the live stream, so you can just go and click it there. And yeah, okay. So today we're gonna start with the beginning of the history. So we're gonna look at the von Neumann cellular automaton. So the goal for today is to explain how it works, why it was designed this way, and at the end we're gonna hint on this we're gonna go through the steps of how to construct a self-replicator. We're not gonna do it explicitly, but we're gonna convince ourselves that it is possible, essentially. And as usual, you can ask questions by voice or by sending it on this thing, and I'll let you know when there are some things to answer. Okay, and the reference I'm using here is this book, which is quite rare, but I think you can find the PDF on the internet, right?
No.
No? Okay, so it's very rare. And okay, it's from Berg. So if you remember, one of the founding guys of the field of artificial life, which had this only group working on artificial life for a while. And it's called Essays on Cellular Automata. It contains several essays that talk about self-replication. And it has I think 2 essays at least that talk about the von Neumann machine, and it's kind of the best resource to know how it works. Well, from today, this will be the best resource to know how it works, but before that, it was the book. All right. So if you recall, last time we introduced this concept of kinematic self-replication, right? And this will be the starting point for today. So just to remind you, the idea behind this is that you have a replicator, which we call R. It's floating into a sea of its own parts, okay? You can be high-level parts or lower-level parts. You have muscles, sensors, computing elements, and so on. And it carries it with it. I mean, it's part of the replicator, really. A tape that contains a blueprint for itself. Okay, a blueprint for itself. And so it looks at the tape and looks at what piece it needs to collect next, waits for it to float by, grabs it, and then assembles it as written in the tape, and in that way it can reconstruct itself. Okay, and then there is this pseudo paradox that arises, which it seems that this is not enough, because if you want to replicate itself, it should also replicate the tape, right? It's also part of the replicator. And so it seems that you need a blueprint for the tape, okay, which I will write a tape for the tape, right? T of R. And of course, once you have this thing, then it seems that you need a blueprint for this, and then you have T of T of T of T of T, and you never end. And as we'll see, not today, okay, let's say tomorrow, next week, you don't need this infinite amount of tapes. You can kind of design the tape very cleverly such that the tape, the blueprint for the tape is the tape itself, okay? So you break this infinite recursion of tapes. The tape of the tape is just the tape itself, okay? And so the idea is actually very simple, okay? The idea is just copy the tape, right? If I have the tape, I don't really need a blueprint for the tape. I can just look at the tape and I know how to copy it, right? Don't need something describing to me. So this is kind of the high-level idea. So that's great, right? But this is not at all rigorous. So we don't know what these parts are, okay? What does it mean to have a muscle part? What does it mean to weight? How precisely should the tape describe where to put the piece, right? Should it say like at the atomic level, you should put it here, or should it say, should go next to this one? And so to get a more rigorous, let's say, setting to create or study this self-replicator, we will do this in an artificial world, which will be a cellular automaton, okay? So cellular automaton, let's go over the definition again. The cellular automaton are intrinsically a discrete world, right? So the world is first composed by an n-dimensional grid, we'll restrict to 2 dimensions for today. So you have grid of boxes, of cells, and each cell in this grid can have a finite amount of different states, right? So take the example, if you recall, of the game of life. You have a 2D grid of cells, and each cell can be in 2 states, right? Either on or off. In general, you can have more states, okay, which we denote NS, the number of states. And here I use a lot of the mathematic like definitions, but it's not really important to really understand all these things if you're not used to this, to these very like rigorous definitions. But yeah, so when we'll talk about a cell next, what we will mean is both the location of the cell and the state of the cell, right? So that's what you need to fully describe a cell. And so if you need to fully describe the world, it just means fully describing all of the cells of the world. So it's just a mapping where for each position in the grid, so I denote here by Zn in n dimensions, you need to assign one of the possible state, okay? Each cell can be in a single state at once, right? It's not quantum mechanics. So yeah, a few remarks. So usually there is some sort of a special state, like which is called the blank, quiescent, or ground state. And usually we call this state like this because when a ground state is surrounded by other ground states, it just remains a ground state. So it's kind of inert, right? It's a vacuum, if you want. And so if you have such a special state, you usually work with world states where at least at the beginning, only a finite number of cells are something else than the ground state. Okay, so there is not only a finite amount of stuff, if you want, when you start off. Right, this is just so. Anyway, we can look only at a finite part of the world, so it's kind of useless of having an infinite world. This is kind of the idea. But the world is usually taken to be infinite, so you can infinitely extend, right? If you send a cell somewhere, it just goes on forever. Okay, so this is the definition of the state of the world, but obviously we need to add some dynamics. So we need to say, how does it evolve in time? So for this, we define the notion of a neighborhood, which is very intuitive. So the neighborhood is just a region of space which determines which cell can interact, okay? Because the interaction, yeah, so that's one of the things, like one of the properties of the cellular automata, is that the interactions are local, okay? Usually the cells can interact only with some fixed amount of cells around them. They cannot interact with a cell which is arbitrarily far. And this is kind of taking inspiration from real life physics, where, at least as far as we know, physics is actually local, so everything happens at the same point. Okay, you could argue for entanglement maybe, but it's some strange notion of non-locality. So here we are local. And we will consider also, that's another constraint that we put ourselves, cellular automata where the neighborhood does not depend on which cell you look at, okay? You could imagine some cellular automaton where, okay, if cell is in state 1, then it can look very far away, but if it's in state 2, it can look only very close. Or, for example, in this part of the world, somehow there is no fog, so cells can see very far away. And in this part of the world, there is fog, so cells can see only very closely. We are not going to do that. We're going to assume that everywhere, all neighborhoods are the same. And this is also kind of an idea that comes a little from physical plausibility, whereas we think that physics is translational invariance, right? So the same physics apply here and on Mars, right? The physics does not change according to where you look. That's the same idea. And so, okay, and then the neighborhood formally is just a subset of Zn, of the world, right? And so if we are given a cell C at some position X, what we say is that it will be allowed to interact with cells that are located at X plus N, or in other words, just with the cells that are in its neighborhood, okay? So when we write N of C, this means just the cells in the neighborhood of cell C. And okay, just a few notes. A cell itself can be in its own neighborhood, right? This is not forbidden. So a cell can influence its next state. And okay, this is not important. Okay, so the two neighborhoods which are most common in cellular automata, at least the most standard, is these two. So the von Neumann and the Moore neighborhood. So the von Neumann neighborhood is this one. So that's the one we will use for von Neumann cellular automaton. And this is the Moore neighborhood, which is, for example, the one used in the game of life, right? So this means that when you're a cell here, you're allowed to interact with these 5 cells. Right. Okay, so now we have the neighborhood. We know one cell with what other cells it can interact. Now we can introduce dynamics. Okay, so for now, the CA is totally inert. It does not evolve in time. And so we introduce some rules. So first of all, something I didn't write, right? So time is discrete. We have discrete time steps, right? So we don't have a continuous time. We have time 0, then time 1, then time 2. Okay, so in cellular automata, at least the classical definition, the space is discrete and time is discrete as well. Okay, again, to capture the notion of locality, translational, that I already said, yeah. If we want to be local, we assume that each interaction happens at the level of the neighborhood. And we want to preserve this transitional invariance. So not only will we impose the neighborhood should be the same everywhere, but also the evolution rules should be the same everywhere, right? And when I talk about physics of the world, I just mean the evolution rule, right? The evolution rules, right? So to denote this time, we introduce a time variable. And so we will denote WT, the world at time t, right? After t steps of evolution. And so one thing we must choose is the initial condition. So the initial state of the world, which we denote W0. Okay. So then it's very easy. We have WT. What we need to know is give some physics or some dynamics of how to get from WT to WT plus 1, right? It's very intuitive. And so what we do is that we take each cell of WT and we apply some evolution rule, which is this transition rule here. And so the transition rule, what does it do? So it takes the neighborhood of a cell. Right. So here we define the neighborhood just as the position of the cells. So to be more frank, it takes the state of the cell in a neighborhood and it assigns a new state. Okay. So in other words, you pick a cell in your world, look at the cells in the neighborhood, and you apply this function that tells you, okay, the new state of this cell will be such and such, right? So this is what I write again. So to compute the world at t plus 1, for each cell CT, so now we denote because it's cell at time t, we compute its value at time t plus 1 by just applying this transition function to the neighborhood of this cell, okay? And so an important thing to note here is that you will notice that C at t plus 1 depends only at C at time t, right? So you can compute all the states of the cells at time t plus 1 independently. They don't depend on each other, right? So this computation here can be completely done in parallel in terms of the world, right? Not in time, not in parallel in time, but you can compute the new states of all the cells in parallel, okay? And yeah, here I just repeat that usually if you have a full neighborhood of quiescent or ground state cells, the update rule leaves the cells in the ground state. Yes?
Yeah, so that means that the evolution is synchronous, basically.
Yes, exactly.
But we could also consider like some kind of asynchronous evolution.
Yes. So the question is, the evolution here is synchronous, and the answer is yes. And you could, of course, consider some asynchronous cellular automata where some cells, maybe they have a rule to determine how fast they evolve, or you don't update all cells at once, etc. So you can extend that a lot. But here we're going to try to keep everything completely deterministic and very simple, just so that we are able to conclusively prove that we can build this self-replicator. Okay? Other questions? All right. So now the von Neumann cellular automaton. So it's just an example of such a cellular automaton. And the way we're gonna, or at least the way von Neumann designed it was very intentionally, okay? This is kind of in opposition to kind of the game of life where you choose some rules which kind of make sense and then you see, oh wow, it makes a lot of cool stuff. This is completely different. Here, von Neumann chose very precisely the states and the dynamics because he had a very precise goal in mind, which was to have rules that allow you to build a computer, okay? And so, yeah, when I mean computer, I just mean Turing machine, which we'll define next week. And next week, we'll also show you that having a Turing machine allows you to, implies that you necessarily have, with some caveats, self-reproducing programs, okay? So essentially what von Neumann said, okay, then I don't need to kind of think really hard of how to build a self-reproducing machine. I just need to know how to build a computer, and then for free, I know that I have a self-reproducing machine, okay? So what do you need to make a computer at a very simple level? You need circuits, okay? You need some way to carry the information from one part of the computer to another. You need computing units, so the processor if you want. And here we want to make very simple processors. And you can show that if you can make the NAND gate, okay? So a gate is just something that takes two inputs that are either 0 or 1 and outputs either 0 or 1, okay? So the NAND gate, here you have the table from what are the inputs, what are the outputs. And what you can show is that if I give you a NAND gate, you can essentially create a circuit that computes all functions that are computable, okay? That's all you need. That's quite impressive, but that's all you need. And so a NAND gate in particular is composed by a NOT gate that just inverts your input and an AND gate, which take the end of your two inputs, right? So for computers, you also need something else. You need some way to store some information for use later. So this is memory, we call it. And then there is an extra requirement, which is not really necessary to have a computer, but we want this computer to be able to reproduce itself. So we need the ability to create new non-quiescent state, right? Because if you start with a world that has like 20 non-ground states, if no other states can be created, you will always have 20 non-ground states. So even if you have a computer, you can't do anything with it. So we must be able to create a new matter because we don't have this sea full of matter floating, right? We actually need to create it in this point of view. Right. So with these constraints in mind, von Neumann introduced 29 states, which are separated among 5 classes. Okay, and now we'll present the states. So you have 8 ordinary transmission states. So let's start with that. So the ordinary transmission state, will represent them like this. So you should see those as arrows pointing in the 4 cardinal directions. Okay, they're just blue arrows, and they have 2 possible states for each direction. They can be either unexcited, which is the top row here, or they can be excited, like this one here, which we denote with a yellow dot on it. Okay, so you can imagine this yellow dot being an electron or a photon or whatever. It's some particle, and the evolution rules for this ordinary transmission coefficients, we'll call them OT, are very simple. So they just, when they are excited, they just transmit the excitation in the direction they are pointing to, okay? So if the OT points to another OT, the excitation is just transmitted in the next time step, okay? And here there is some technicality that if you have several arrows pointing towards a third arrow, then the receiving arrow will get excited whenever any of the pointing arrows transmits something, okay? So in other words, if you want, when you have an arrow with 2 other arrows pointing on it, the middle arrow is doing the OR operation on the excitations. Okay, we'll see some visualizations if that's not clear. If you have 2 OT arrows that point at each other, in that case, the excitation is just dissipated, right? They cannot transmit if they point towards each other. And then you have more interaction with the other states, which we'll see later when we present them. So here I have a video that kind of presents this. So here I have a, okay, let me stop it to present. Here I have just a square of arrows going in circle with two excitations. So here you can predict the excitation are just transmitted along the circuit, right? So they will just turn around the circle. And here it's just to illustrate the fact that, so here I have two cables wiring in a third cable. So this arrow here will just transmit any excitations that arrive from either the left or right, okay? And in the end here I have two arrows pointing toward another, so here the excitation will just disappear. So I think concentrate on this thing to see what happens. Right, so as you can see, the excitation are just transmitted, this works well. And so here, just to notice, so here the two excitations arrive at the same time on the arrow, and in that case, it also just passes through, right? So you lose one excitation, but it just passes through, okay? Right, so that's very simple. So you see that this is very intentional. Why do we need these arrows? Just to make some circuits, okay? We can transmit some electricity or something towards them. Then you have the special transmission or ST states, which are again arrows, but they are now red. And they can also be either excited or not excited. And they follow mostly the same rules as the OTs, right? So they can transmit excitation along red paths, etc. So yeah, if the ST points to another ST, the excitation is transmitted. If two ST arrows point at each other, then the excitation is dissipated. And the key difference, because of course we wouldn't need it if it wasn't different from the OT, is that when an ST transmits an excitation to an OT, it destroys it, and vice versa, okay? So you can see like an analogy that Clément made last year is that these blue arrows represent like the kind of the West, the USA, and then you have the URSS, which are the red arrows. So they can transmit information among themselves, but as soon they transmit to the other side, it just destroys it, okay? So they are kind of antagonists. And right, so we'll introduce the confluent state next, but the special transmission, they also kill the confluent state. So here I have a video. I don't know why I cannot, let me see, yeah. Okay. So here again, you have the circle, this will go around. Here, the same visualization for the ST, just to show they work the same. And here I will just put some excitation on this string, and here you should expect this to destroy everything as soon as the excitation arrives, right? So, okay, this works the same, and then if you look here, right, so the STs, they're used to destroy stuff, okay? And I didn't show it here, but okay, if you act with a blue arrow on an ST, it will also destroy it, right?
So the excitations on the right, they come from you.
Yeah, so the excitation from the right are not from the dynamics. I just have some interactive system where I can just add excitations where I want, okay? So these, they were not created from thin air, yeah, good point. Okay, so then we have quiescent state or ground state. So these you have already seen is the black ones here. So these are just the ground states. They essentially have no interaction with anything. The only thing is that whenever they receive an excitation from either an ST or an OT, they will transition to the sensitized state, okay? And we'll see that's how you build states. But that's all they do. So the ground state just remains ground state until it receives an excitation, then it kind of wakes up. Okay, now the confluent states. These are a bit more complex than the arrows. So they can be in 4 different states, which are depicted here, okay? And the purpose of the confluent states that we will see is twofold, okay? First of all, they can act as an AND gate, okay? When you have incoming excitation, they will do the AND operation on the excitations. They will also be used, actually three uses. They will also be used to multiply the amount of excitations. You can use them to turn one excitation into 3. And they can also be used to delay the propagation of excitations, okay? So we'll see how. So they come in 4 versions, and the way you should read this is that here is the empty confluent state. This is a confluent state that just received an excitation. This is a confluent state that received an excitation 1 tick ago. So kind of the way I see it is that the excitation arrives in the middle, and then it propagates outwards, right? And then this state is, of course, if you have an excitation, it propagated and you receive the second one, okay? So we'll denote them by 0, 0, 1, 0, 0, 1, 1, 1. And of course, this one means just received an excitation. Here it was received the tick before, and here both, okay? So, right, so this is just what I explained. C0 is the default unexcited state. C00 will transition to C10 if it receives an excitation from an OT, right? And the excitation from the ST just kills it. And here is the thing to note, right? If you have several arrows, OTs, incoming to a confluent element, it will do the AND operation on the incoming arrows. Okay, so if you have two arrows incoming a confluent state, and I send an excitation from the right, it will not turn on. I need to send a simultaneous excitation on the right and left, right? Because it's doing the AND operation. And so here it's kind of not so clear, but if there is nothing around the confluent state, it does not enter this AND operation, right? To qualify for the AND operation, you need some arrows that go in. Okay, and then it's very simple. So when it receives an excitation, it goes to C10. Then if it receives no excitation, it goes to C01. If it receives one from here, it goes to C11. Okay. And then the last thing to say, right. And so when you get to this or this state, in the next tick, the confluent will emit the excitation it has stored in all four directions, okay? So that's what happens. You receive an excitation in the middle, it propagates to the sides, and then it's emitted on all sides, okay? So that's what I write here. So if you have CI1, it transitions to C0I or C1I, depending on what it receives. Yeah, and so when that happens, you see this one was on the exterior. The confluent will emit excitation in all four cardinal directions, okay? And if there are STs or OTs which are not pointed toward the confluent, as usual, you cannot receive something from where you point, then they will be excited, okay? So here is note. So in this way, let me just see. Yeah, I was just wondering if I was recording. So in this way, the confluent element can act between a bridge between OTs and ST. So you can see kind of like it's Switzerland, right? It's a neutral state. You can send it a message from the OTs, it will store it, then emits it, and it can emit it to an ST, okay? So in that way, you can kind of communicate between blue and red, but not the other way around, right? So the red one cannot send an excitation to the confluent, it will just kill it, right? And so, yeah, so the excitations that are emitted by the confluent do not excite the quiescent or other confluents, okay? So this is a lot of to take in. So let's just look at this, which showcases kind of everything. So what do we have here? So we start with a single excitation here, right? Which will arrive at the confluent. So the confluent will store it for one tick and then emits it in all directions, okay? So here, only this arrow and this arrow will get excited because these two arrows are pointing towards the confluent, okay? So the first excitation will go around here and then back to the confluent, but since it's at ST, it will kill it, okay? The second excitation will go here, and here it will be just slowed down by the confluence because each confluent takes 2 ticks to re-emit the excitation, right? Whereas the arrow just takes 1 tick. And these confluents on the side are just to show that when the confluent emits its excitation, it does not excite the other confluents, okay? So the excitation goes through here, and here it takes 3 paths of different times, right? They take different time because of the number of confluent and the length. And then they join back here, and here we'll see that the confluent here will make the AND operation between these 3 arrows. So it will only light up if these 3 arrows emit excitation at the same time. Okay, so let's see it. Excitation goes here, it's emitted. So focus on this one first, it should get destroyed, right? And now if you look at this one, right? So here the excitation is about to enter the confluent, but these two arrows are empty, okay? So the confluent will just not get excited. So we get nothing on the other side, right? These three excitations were not synchronized. The only way to get something on the other side was to light up these 3 arrows simultaneously, okay? So, right, so we see that with the arrows and the confluent, we have access to the OR and the AND operation, okay? This is not enough to build a computer. We need the NOT operation, which we don't have yet, okay? So the last state is kind of the most complicated, but it for no good reason, actually. Just a second, because my computer is about to turn off. Okay, so the sensitized state is is how you build new states, right? Until now, we saw ways to interact with states and destroy states, but we were not able to build new states. So the sensitized state is kind of complicated. It comes in these 8 variants, okay? And the way to create a sensitized state is just to send an excitation from an ST or OT into the void, okay? Then you will create this state here, S. And then the following states, the way to build them is really easy. So the red crescent here means that the state received no excitation. And the 3 crescents denotes the step 0, 1, and 2, or 1, 2, and 3. Okay? So S0 is if it has just not received an excitation, whereas S1 means it's just received an excitation. Okay? So let's say I create a sensitized state and then I send 3 excitation in the next 3 ticks. It will go from S to S1, then receive another excitation, so it goes to S11, and then receive to another excitation, and then it will morph into a state. Okay? So for example, this one here means that you created S, and then for the following 3 ticks, you didn't send anything, okay? So, okay, this is the written state of that. For when you create the sensitized state, for each subsequent tick, if the sensitized receives an excitation, it evolves from S to S1. If it receives no excitation, it evolves from S to S0, and then you keep piling up the zeros or the ones here, okay? So we write Sijk or Sijkl, where Ijkl is the sequence of bits it received, okay? 0 for no excitation, 1 for an excitation, okay? And do note that this Sijkl does not exist as a sensitized state, okay? It's not a real state. It's just the series of excitation it received, okay? And the way it works is just that you encode essentially which state you want to create in this sequence of bit that you send, okay? So these are the list of each sequence of bit that you need to send after creating the sensitized state to get each of the possible states, okay? So let's make an example. I create a sensitized state, okay? I am here. And then I send nothing at all, okay? So what will happen is as a sensitized state, we go from here to here to here to here. And then it still looks at what it gets in the next step. It receives 0. So in the next step, it will become an east-directed OT, okay? Same thing, if you want to create a confluent, you first create a sensitized state, and then you send it how many? Yeah, 3 excitations in a row. So the S will go to S, S1, S11, and then it still records the third one, even though S111 does not exist. If it gets a 1, it will go to a confluent. If the last bit was a 0, it will go to a south ST, okay? So this is how you create new states. And note that you cannot create all 29 states, but this is not necessary, right? These 9 states are all the base states that we need, and then the other ones can just be obtained by adding excitations or whatever. Right, so any question on this? So let me just try to whoops. I want to take a screenshot of this thing because we'll need it later for the quiz. Yeah, give me a second. Or I'll just take it up in when we have the quiz. All right. Okay. So note that not all states are generated in the same number of ticks, right? So for example, the confluent, you need to create a sensitized state and then send 3 ticks, whereas the east OT, for example, you need 4 ticks to create it, okay? So it's not very symmetric, but you cannot make a mistake, right? If the confluent receives only zeros, it knows to wait for a 4th tick before morphing, whereas if it receives ones, it will morph on the 3rd tick. So there is a big asymmetry between states. Okay, this is not very natural. So if you wanted kind of a physical, plausible world, it would make sense that it's not harder to produce an arrow going down than an arrow going left, right? Here it's harder, but it doesn't matter, okay, because we don't need something that will evolve on its own or it's very natural. We just want something to design a computer, okay? And yeah, last note is that you can use excitation both from OTs or STs to produce these new states. You cannot destroy when you create a sensitized state before it's born into something, okay? So here I have just a video illustrating that. So here I have a series of circuits which I've prepared with some excitations. And these, you have 9 circuits. And these are the 9 excitation strings that you need to send to produce each of the states, okay? So you note here that you have the first excitation for everybody to create the sensitized state. And then according to the code you received afterwards, in these 4 trailing arrows, it will determine what states you get. So let's see it. Right, okay? So here I did not animate I didn't bother animating the quadrants because it was a bit too much work. But you can see that, yeah, maybe I can catch it. Yeah, okay, you can kind of see it if you're fast. The last 2 arrows take 1 more tick to produce, right? But okay, we can create all the states. And so now we are kind of good. We can create stuff, destroy stuff. So now we can start thinking about how to make a computer, okay? So the first question is here. So yeah, I will have to get the screenshot first. Yeah, perfect. Tac. Oops. Oh, why does it want to let me? Ah, yeah, perfect. Okay, so I'll leave it here on the screen. So you can go on the Slido if you want and try to guess. Okay, let's not spoil it. So you have this thing here, this initial condition. You have to guess what is the state. Oh, sorry, I have to launch the poll. Yeah, okay. So you have to guess which state will be generated in this place. So I'll leave you 1 minute to figure it out. If you have a piece of paper, it might be useful. Okay, we have a few answers coming in. Wait a bit more for everybody to kind of think about it. So by the way, yeah, if you reminder, you can access to answer polls, just go to slido.com and input this code. Okay, there is some disagreement, I see. Right, let me wait 20 seconds more and then I'll reveal the answers. All right, okay, let's take a look. So I can show you the results. Yeah, let's see. I'm not logged in. Okay, whatever. So you should see the results of the poll on your app. So I don't remember the answer. So let's just see. Oops. All right. So the confluent duplicates. All right. So the answer is the east directed OT, and 60% of you got it right. That's very good. So let's go on a bit on how you should think about it to compute these things, right? So you start with one excitation, it goes through a confluent, and the confluent will just distribute it to these two arrows, right? So you can just forget about the initialization, you just start with an excitation here and here. And then the key is to understand what series of bits will go in this thing, right? And to do this, you just look at all the possible paths for the excitation, and you compute how much time it takes for the excitation to get there, okay? So if you start from here, you will get, so 1, 2, 3, 4. So it'll take 4 ticks to get there. And from here, it will take 1, 2, 3, 4, okay? So the excitations arrive at the same time. So the first excitation, we said it just creates the sensitized state. In that case, okay, we had 2 excitations, but they arrive at the same time. So it just counts as 1. That was kind of the trick question. And so you can make a sensitized state and then give him nothing, okay? So this corresponds to getting 0, 0, 0, 0. And so you get the east OT in this case, okay? All right, so let's go to question 2. Very similar. A bit more complicated. Whoops. Right, so let's see if you can guess what state you get there now that you know kind of the way of thinking. Okay, we have a few answers coming in. By the way, the length of this is not just to annoy you with a number of arrows to count. It's just that it's really tricky to condense these things into little little things. Okay, let me wait for 5 more answers and then we can look at the results. About the same success rate as the previous one. Or at least I think. All right. Okay, so here we have 40. Okay, it's kind of unclear. So let's go through it. I might know where the problem is here. So let's look at the video and then we'll explain what's happening. Okay. All right, so the answer was north ST. Okay, most of you got it right, but it was 40%. So there was kind of some misunderstanding here. So the first thing to see is, yeah, it's kind of, the confluent is kind of difficult to count at first, but it's really just 2 ticks. Okay, so let me try to count the upper direction. So in the upper direction, again, we start here and here, no need to consider this one. So first of all, if you look at the circuit, you know that you will end up with maximum 2 excitations in output. So you can immediately rule out these ones, right? Because they need more than 2 excitations, right? Because to this string, you need to add the first excitation that makes the sensitized state, right? So here, the first root will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay? And the second one, okay, I counted the first one here, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I counted 12 for the previous one, I already forgot, right? So they arrived one after another, okay? So again, the first one is just to make the sensitized, and so then we get immediately 1, right? So we have the north ST. So here the mistake not to make is that the confluent does not transmit to other confluents, right? So here you do not get an extra excitation from this confluent, otherwise it would get pretty messy. And by the way, that's one of the reasons you cannot do things really compact, because okay, you need some sort of delay, the minimum delay to synchronize all your paths. Because you see the path that goes down, it will naturally have some delay because of this longer path, right? So you need to counteract this with more confluence so that you can kind of synchronize them. So it's not that obvious. And okay, I have a last one that I will leave during the pause, which is a bit more complex again. And it's this one. So I will activate the poll and then we can come back after the pause to see what this one is. Yeah, so we start at 3:15. Oops, just a second.
Une autre instruction, genre R.
Okay, so I revealed the answer. Let's look at it. So here there is not really whoops. Let me rewind. Okay, so here we see 3 paths, and if you follow them, you'll see that you actually get 3 excitations. So here you have more possibilities at the end. So if we play it out, okay, you get a south ST, and now most people got it right, 73%, pretty good. Okay, so some people, the second most voted was the confluent element, and I can understand why. So indeed, for the south ST, you get 3 excitations in a row, but don't forget the first excitation that you use to make the sensitized state, right? So if you want to make a confluent, you really need 4 excitations in a row, okay?
In total 4 pathways?
So let's look at it again, but I don't think so. So
Wait, I mean.
So where is your misunderstanding? So this, yeah, the top one.
Split into 2 paths, one continuing straight.
No, because the arrows. So here, yeah, let's look at the top. Okay, that's important. So here the confluent is gets. It will emit all around. So remember, it's a von Neumann neighborhood, right? So only in the cardinal directions. So this arrow receives it, and then the arrows just transmits where it points. And then again, right? The arrows do not transmit around, only where they point. So if you look at it, yeah. So it goes to this arrow here, and then, so you only have 3 paths. Okay, great. But that's good. These exercises are here to clear any uncertainties on the rules, because they're not that easy. Okay. Right, and so as I was making this kind of little exercise, I realized that it's not that easy. And so if you want a fun challenge, try to design a circuit that makes a confluent element, okay? It's kind of harder than this, because here I start with 1 excitation and then I immediately get the number of excitations I need. For the confluent, you need 4 excitations. So you will need to have some other splitting somewhere else. And then you will see that you want to send them one after another. So you need 4 paths that kind of spread out. But the more you spread the path, the longer they are, then you have to add more confluent, then it takes more space. So it's really non-trivial to make something compact, at least. But you can convince yourself that you can always do it, okay? All right, so now, so these circuits already, they are kind of some special circuits, right? It's a component that when you send in 1 excitation, it creates for you the proper state that you design, right? So it's kind of a little factory for specific states. So now let's build some more generic circuits, okay? So we want to build a computer. And for this purpose, we need at least to be able to emit and recognize, or at least, maybe not at least, but it's one way to do it. We need to be able to emit and recognize a specific series of bits, okay, that represent something in coding, okay? You need a way to tell, okay, I want to read this sequence, I receive this sequence, I do something, okay? So the first object that we create is the pulsar. And the pulsar is just an object that when you give it a single input excitation, it will output some series of excitation that you choose, okay? So in some way, these things we build, they are pulsars, right? So here, if instead of putting a ground state, I just put an output arrow, we indeed get something that when I give it one excitation, it outputs the string 111, right? So this is all it is. So, right. So this is useful because you could represent some specific instructions. So for example, you have a cable here. When you send an excitation here, you encode, you construct a north ST, as we have seen, okay? And to construct the pulsar is essentially what I showed you before, okay? You start with one input excitation, okay? And you first start by splitting it into as many excitations that you will need, okay? So if the pulsar is 10101, you need to turn this excitation into 3 excitations. And then you construct kind of some little highways for these the excitations that you constructed, and you delay them using either some convoluted paths of arrows or some confluent to delay their arrival, such that they arrive at the appropriate times in the output, okay? So one thing you cannot really control is how much time will the pulsar need to produce the output excitation, right? If I want a pulsar that outputs like 2 million, a string of length 2 million, you will need a pulsar which is humongous, right? To be able to kind of delay everything in increments of 2 millions, but you will be able to do it, okay? So we will construct a computer. We never said we were construct a efficient computer, okay? So we'll give it as much time as it needs to do whatever it wants, but it will do it eventually. So this is an example of a pulsar, and this, okay, let me skip this question maybe because we're a bit short, and we'll do it in the end if we have some time. So this is an example of a pulsar, okay? You just have a in location where you input your incoming excitation, and then you have an output location which outputs some string, okay? So here is the pulsar in action. I'm debating to show it because it's the question, but okay, let's see it. So it's exactly the same as before, right? So you send an excitation, and this one is quite compact. Right, and then it's routed, and then it outputs some excitation. I will not spoil which one, because it's the question, but okay. So you should be convinced now, and if you're not, let me know what is your worry, that you are able to create a pulsar for any sequence of excitations, okay? If you are given enough space to make your pulsar and enough time for the pulsar to work, right? And this is because simply you have confluent elements which delay signals by 1 tick. So you can access all delays using that. And you have as much space as you want. So in a sense, if you need 1 million channels, you can just create 1 million channels like this. And of course, the channels on the side will be much longer than the channels in the middle. But you can counteract that by putting confluent elements in the middle such that they are still synchronized. So you might be worried, and I guess that's a legitimate worry, that at some point you have some runaway effect. Like as you get the channels that go on the side, they are so much slower than the channels in the middle, yeah, that you don't have space to put confluent elements for them. And yeah, I'm not sure how to answer this worry. I think if you think about it, you can show that it's not the case, but it's not obvious because you can just eliminate the channels in the middle, and then you put pulsars on the side. Okay, it's not that clear.
You can always make them longer.
Well, you cannot because you're in this box of right? You're like constrained in the middle. You cannot. You have all these channels going like this. So the channel in the middle cannot you could go like this. Okay. So you can do it. It's true. The way to show it is probably you start looking at these paths and you see that the delay that you can add grows faster than the space that you need to go around. But okay. And so the notation we have is that we write P of 10111 for a pulsar that generates this sequence of excitation whenever you input a single excitation, okay? And the way we will use the pulsar is that you put an excitation in, you're not allowed to put another excitation until the string goes out, right? Because it might mess up something in the circuit. Okay, the second element we have is kind of the opposite of a pulsar. It's a decoder. And the decoded, what we would ideally want it to do is, given a certain sequence, it will output a single excitation if it is the correct sequence. Okay, so it recognizes some string, some arbitrary string. Okay, so this is kind of not so easy to do, and we'll see right away why. So we'll start with first a simpler version. Okay, so it will be an element that recognizes. So that fires, we'll say that recognizes, if it receives a sequence with ones at specific locations. So what do I mean by that? If we have a decoder for the string 10101, it will fire whenever it sees these 3 ones, okay? So it will fire for this thing, for this thing, for this thing, but it will not fire for this one, right? This one is missing the 1 at this location here. So it's not perfect, okay? It does not recognize our input sequence perfectly. It recognizes only the locations of the ones, okay? And the thing we are missing here for now to make a true decoder or recognizer is the fact that what you would ideally want to do is to do an AND operation in all these digits. So we want this one to be 1, and this one to not be 1, and this one to be 1, and this one to not be 1, and this one to be 1. Of course, in this sentence, I said not twice. Okay, so we need the not gate. Because you can use the confluent to do 1 and 1 and 1. So you can detect when there is a 1. To detect when there is a 0, you need to detect when there is not a 1. Okay? And so we need the not gate. So that's why we start first with the simpler version that does not have a not gate. Okay? So this is how you build a decoder, okay? So the simple version. The key idea is that you will use the confluent elements to make this AND operation on where you want the ones to be, okay? So this is an example for a decoder for the string 10101, okay? So let's see how it works. So here I input A, B, C, D, E, which can be either 0 or 1, each of these. And then I make different paths. And instead, just like in the pulsar, but here, instead of just sending the path to an output, I send the path to kind of intersect at the confluent element. Okay? So for example, here I have a path that takes length x plus 2, where x is whatever number, we don't care. And here I have a path which takes x ticks to arrive to this confluent, okay? So what it means is that this confluent will do the AND operation between A and C. And then it will do it between B and D, and then between C and E. Okay, so again, if we count the size of this path is 1, 2, 3, 4, 5, 6, 7, 8. So you have one bit arriving after 8, and the other one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So this confluent here verifies if you have a 1 at space x and space x plus 2, okay? All we need to do to detect 10101, you need to detect if there is a 1 at x, x plus 2, and x plus 4, okay? So that's what we do, okay? So here, the output of this confluent is x and x plus 2. And then we make yet another path, which takes x plus 4, and combine it with the first one, okay? So the output of this last confluent element here will be x and x plus 2 and x plus 4, which is the end of x, x plus 2, and x plus 4. Okay. So it will fire only if you have exactly a 1 at position x, x plus 2, and x plus 4. Okay, let's see it in action. So here I send the correct sequence, so 1, 0, 1, 0, 1. Okay, and then a bunch of stuff happens. Okay, it's kind of difficult to keep track because you're just sending all these excitations one after another. But you see that here. So here the thing detected that there were 1, 0, 1, but okay, yeah. Now it's kind of harder to explain here, but what you will see is at the end, okay, you have a single pulse coming out of the thing, right? It's when the full things were synchronized to go through. And okay, let's try with other, yes, question?
Nobody checks if it's one, like there are alternate ones, right?
Yes.
Even if it's 1, 1, 1, 1, 1.
Yes, precisely. Okay, so the question was, this checks only if there are alternate ones, and that's correct. This is not the full decoder, it's kind of the simple version, which just checks, you just impose some locations for the ones, and the rest you don't impose anything. So let's see it exactly. So here I give a string with 5 ones, okay? And this in particular satisfies the condition. It has 1, 1, and 1 at position x, x plus 2, x plus 4. So we should expect this to fire a single time. So let's see it. And it's kind of crazy. When you see what's happening inside, it feels super strange. But since we designed the thing correctly, we indeed get 1 pulse out. Okay, so it detected it correctly. Yet another example. So this one should not fire, okay? Because we do not have 1, 1, and a third one spaced by 1 bit, okay? So if we send this in, we should expect nothing to come out the other end. And that's correct, okay? So you see that the way we are designed it is very simple. Then the way it works, it seems much harder, but yes.
What if you have like 7 excitation with
right. Okay, so the 7 excitation, what it will do, it will apply it at all possible translations of the, so it will first consider the first 5, and this will produce an excitation for you or not. Then the next 5, then the next 5, and so on. Because all it does, it's when it receives 5 bits, it tells you if you have 1, 1, and 1. And then if you send it as something longer, it's like you sent 5 bits several times, okay? So it works. And you kind of like preceded the question. So here's the question. Given I have the decoder, the simple one and not the perfect one, 10101, what output does it produce when I feed it this string? I don't think we need this anymore, but okay. All right. So most people got it right. Let me wait a bit more because people on the stream have a slight delay. All right. So the correct answer is, the one intended is 10100. So let me show you the results here. Yeah. And okay, I also included not enough info because I didn't test this in the actual thing. it might be true that for some designs of the decoders, if you like overload it with strings which are too long, it might mess up the things if you do something really clever. I don't know. So I would have accepted also not enough info. But the answer I was waiting for is this one. And the reason why is because when you feed it this string, the decoder, the decoder doesn't inherently has a finite input, okay? It just compares things at position x, x plus 2, and x plus 4. So here we can see it like this. We can see it as processing first this string, and this string will hit, right? So this will produce one excitation. Then one tick after, delayed, it will process this string here. This one does not satisfy the condition because it starts with a 0 for starters. And then with one more tick of delay, it will process this string here, which also qualifies, okay? So what I expect a decoder which is not built with some extremely clever trick of super compact or whatever, it should output an excitation for the first detection, then no excitation for the second one, then an excitation after, okay? So the answer is 1, 0, 1, and then nothing, okay? Good. Okay, so let's continue on our path to build some computer. So it's usually useful for computation to have something like that can tell the time, okay? Something that you can use to synchronize some components or whatever, or something that produces a periodic output. And this is very easily achieved using clocks, okay? You have all manner of clocks. And the concept is very simple. You just made a loop. I showed you already loops. And then you can choose kind of the clock time by putting some confluent elements or by stretching or de-stretching the clock, okay? And here I have several examples of clock. So one curious one is this one, which seems frozen. It's just that it's completely saturated with inputs, okay? So all the inputs are going around, but everything is always full, so you don't see it change. And down there you have some potential use for a clock. So here I have a string going around, and this is a string that encodes the east ST. And so each time the confluent passes it forward, it produces another ST. So you have kind of a growing snake, right? And the one last thing to notice is this clock here, which is technically a clock, but it's kind of useless because you have no way to access the excitation which is inside. You have no way to probe it, okay? That's why when you have a clock, you usually put at least one confluent element that you can hook up to an arrow so that you can actually probe the clock, okay? So these are clocks, very simple. And using clock, we create something which is called a periodic pulsar. And it's just a pulsar that is hooked up, its input is hooked up to a clock so that it produces its string periodically in time. And you can choose the period, okay? So we write pp of 110, a pulsar p of 110 hooked to a clock of which we can choose the period, okay? And we'll see that they are handy. Okay, so now let's go to the elephant in the room, the NOT gate that we are missing still. So yeah, so I will denote by decoder the unperfect thing, and by recognizers the one that recognizes perfectly a string. Okay. So there's a discussion that I mentioned before, is that to have a recognizer of a certain string, we must require that we have a 0 at the second and fourth position. And so for this you need the NOT operation. Essentially, you write a decoder, but you wire the 0 through a NOT operation, and then you only decode the ones, okay? The problem with this, if you think a little bit about it, is that all states that we have so far, so OT, ST, and confluent, are excitation non-decreasing, okay? What do I mean by that? I mean that if you have an initial state with n excitation, let's call it Sn, okay? And then we let it evolve and we count the final number of excitation after some time t, okay? What we have is that if our state is composed only of this, and assume we don't have the sensitized state, because this breaks everything, but then if I start with a state which has n plus 1 excitation, it can only end with a state that has more excitations, okay? So to rephrase, if I start with a state with n excitation, let it evolve, then start with the same state, add some excitation, I will always end up with more excitations out, okay? And this is a problem because the NOT gate is typically a gate where if you add one excitation, it will, you can use it to remove excitations, okay? So if you have a NOT gate that has an excitation incoming, I just remove it and I will get more excitation, and this will violate this inequality. Okay, to show this inequality is very simple, okay? If you consider these three elements, and you look at all the possible configuration in which they can get, which they can be composed, you see that if you add an excitation, you can never decrease the number of excitation after a while, okay? So for example, for an arrow, if the arrow has no excitation and you add an excitation, you will add at least one excitation, maybe 0, but at least one. You cannot add things around it to remove this excitation in some sense, except of course if you destroy it, but that's the catch, right? That's how you make the NOT gate. So if you don't use destruction and creation, you cannot do a NOT gate, okay? Yeah, exactly that, okay? So the way you can add excitation to get less excitation out, or conversely to remove excitation to get more excitations out, is to use an ST and destroy some stuff, okay? Imagine you have a crazy pulsar that generates you like thousands of one, and then you have just a channel of ST on the input element. You can just add one excitation on this ST, destroy the input of the pulsar, and then you get much less excitation on output, okay? So that's how you make a NOT gate or something similar. So this is the flip-flop gate, or you can simply a switch, okay? So let's it's kind of a bit more complicated, but let's see how to use it at least. So it has 4 inputs. These inputs can receive excitations. So this is to turn on the switch. This is to turn off the switch. And then this in is where you send excitations. And when the switch is on, the excitation will carry on the output. And when the switch is off, the excitation will just not be transmitted to the output, okay? So you use these two things to turn it off or on, and then you use it here, okay? Let's see how it works, because it's kind of cool. Okay, so here I have the switch. Here I have the input and the output. So right now it's off, okay? So as I add excitations here, yeah, sorry, I was a bit fast. As I add excitation here, they are not transmitted. Why? Because there is no excitation here, so the confluent element does not work. Now I send an input to the on state. Okay, let's see what it does. Generates a bunch of excitation that saturate this clock here, okay? And this clock is hooked to this cable. So here we saturate the confluent element from the left with excitations. And now it's on. Because now if we send an excitation here, as we'll see, since the confluent element has an input here, it does the end and it passes through, okay? So we turned on the switch. That's fine, but now how to turn it off? Well, to turn it off, you need to turn off this saturated clock. And how you do this? You send an input here. And what will happen is that you destroy it, and then you immediately rebuild it, okay? And now you're back in the off state where you begin with, and you can turn it back on if you want from here, okay? So, yes?
There's a catch to this, right?
What do you mean?
You turn on and off immediately.
Right, exactly. So as usual, all components must be handled with care. So leave them the time to do their stuff. So you cannot turn off and on as you want. If you turn on, you have some lag. You have to wait a few seconds for it to work, and then. But this is not a problem. You can delay everything, right? In principle, also your computer, right? Everything you do, you have to wait for a microsecond for it to work, and that's the same, but you have to wait for 3 seconds. Okay, so we have a switch, it works, and the switch is essentially like a NOT gate, okay? It's very easy to see that you can make a NOT gate if you have the switch, okay? So for the NOT gate, so in principle, if you have a NOT gate with an arrow which has no excitation, you should have a stream of excitation going out. This is not really nice because, okay, we usually want to like control the number of excitations. So we'll make a NOT gate which is slightly different, as I was saying before. So this NOT gate, you first notified it with a single excitation to tell him, okay, I want you to compute for the next excitation. And so you turn it on and then send an excitation and it will apply the NOT operation on this next excitation, okay? So how do we build this NOT gate from the flip-flop? Very easy. So we have the input 1 that lets us know we want to use the NOT gate, okay? So what we do is take this input, duplicate it, and we route it to both the on position and the in position, okay? So with the first input, we turn on the flip-flop gate, okay? Then we have another part of our thing where we decode the first 2 inputs, okay? Sorry, so let me just precise what how the NOT gate works. Gate, works. So if it receives 1, 0, it outputs 1. If it receives 1, 1, it outputs 0, okay? So it's literally a NOT gate, but you have to prepend your thing with a 1 to tell him, okay, wake up, I want to compute, right? So it makes the NOT operation on this second bit, right? So what to do is take with the first bit, with this we turn on the flip-flop and we also put an excitation inside the in, which is delayed. Using a decoder for 1, 1, okay, this string here, we route the decoder to the off input of the flip-flop gate, okay? So what happens? So, and of course we time all these routings in the proper way. So if we receive 1, 0, we will turn on the flip-flop on and the excitation will go to in and so will output 1. Okay, so 1, 0 outputs 1. If we are given 1, 1, we turn the flip-flop on, but then we turn it off with the second output from the decoder. And so we will emit no excitation, so we have a 0. Okay, so we have the NOT gate. It's super complicated, super slow, but we have it. Okay, so from now on, we can assume that we have a NOT gate. Is that good? Let me see the question here. Right.
Just,
yes?
since there is delay, like
yes.
so the thing is first on then off, so it's
Yeah.
still always.
So you have to be careful. So you turn it on, okay? Yes. You wait a long time. Then let's say you plan for the off signal if there is. You plan it to come after 100 ticks, okay? And you plan for the in signal to come after 200 ticks.
Okay.
And then you're sure.
Yeah.
Because the sequence of operation, if you send 1, 1, will be turn on, send the in signal, then wait. After 100, turn off. And then after a further 100, this in signal comes, and then you get your answer, okay? So it's very nice. If you don't have to be efficient, you can assume as much as you want. You can even be super safe, give how many delay you want, and it's fine. Yeah. Okay, so now we have the NOT gate, so we can assume the NOT gate. And so it's clear that we can now build the recognizer, okay? The recognizer is just a decoder, but you apply the NOT gate to the position where you want zeros, okay? And then you have all these problems with the routing and the timings, but this is just technical stuff, okay? But this is also the reason that now I don't have any visualizations because building the thing is actually very tedious, yeah. So we have, in other words, we have access to OR and the NOT gate, and so we have enough to build any circuit. And you might ask, okay, what about memory? And the flip-flop gate is some perfect example of memory, okay? You can just turn it on or off. You can probe it to see if it's on or off. So if you have an array of flip-flop gates, you essentially have a hard disk, right? Okay. So one last thing before we put everything together is wire crossing, okay? So this is maybe not technically needed, but it really helps a lot for what we want to do. And so we're just gonna present it. And that's how von Neumann built his thing. And so a wire crosser is very simple. It's just a thing that has some amount of inputs, some amount of outputs, and it just allows you to connect any input to any output, okay? That's why it's called wire crossing. It's just a place where you can cross incoming wires, okay? Which you cannot really do with usual wires, right? You cannot cross two wires. There is no such thing in von Neumann. Right, and the way it works is represented by this image, which I'm trying to fit in the screen. Okay, so here we have a series of inputs and outputs. So you can differentiate them by the kind of arrow that you have, right? In or out. And how does it work? Okay, let's see. So let's say that we put an input here, right? P is the pulsar, remember. Okay, so the input here will be encoded by the pulsar and will be outputted at the sequence A. Okay, A is just any random sequence. So the sequence will go around here and it will be dispatched in all of these recognizers. Okay, but of course only the RA will hit, right? RB will not recognize A, same for C. Okay, so we go here. Then here we are transformed back into G. Okay, and then we continue going and we are dispatched to all the boxes here. So here F doesn't work. Here the arrow is not in the correct direction. Here G works, and so we output here. Okay, so as you can see, I put an input in A, the A goes to G, and the G goes out here. Okay, so I routed any signal here to output here. Okay, same thing for B, so B goes here, then B becomes F, F is routed here, and then C, okay, C goes here, here, nothing, nothing, RC goes to E, and this goes again around and goes out here, E, right? And as you can see, you can also mix and match. You have an entry A here and an entry A here. They both go out of G. That's fine, okay? So very simple. Question? No? I'm not thinking. Okay. There is also no coded channel wire crossing. And now I have one question, which is a text question. So let's see, I won't make many text questions, but you can actually answer with a small text on the thing if you want. And so the question is, why do we need the component on top here? Okay. You could argue that I can do this and then route the A directly outwards, and then here put a recognizer for A, right? Why do we need this thing to translate A to G and then recognize G? Why don't just feed the A directly? I'll let you think a bit about it. I don't know if people can see the answers of other people. Probably yes. Okay, perfect. Okay, it's an experiment with the textual answers. I don't know if it will work, but if you have an idea of why we need this. It actually does not work without this. Okay, I see 4 people typing, so some people are. Mm-hmm. Okay. Okay, let's wait for a minute more. Okay, one last guy typing. Let's wait for this and then we'll look at the answer. Not typing anymore. Okay, oh. Okay, so let's see, we have 3 answers. So the first one is to avoid messages going in a loop, and I think that is the right answer. One-to-many routing. So the one-to-many routing would work also without it, right? So if I put here a recognizer for A and just get rid of this, whenever I enter here, I would still output here, and same things for this, right? So the problem, which I was careful not to show when I was explaining how it works, is that as you can see, you have a full loop here, right? So if you don't have this thing, whenever you send a message here on the loop, it continues looping forever, okay? And it continues outputting forever. So here, we can have A going in a loop, but you see that each message will always be transformed in something else than these A, B, and C. So at most, it will do one loop. Because let's follow A. So here A will go here, become G. It will output here, but it will also continue going in the loop, right? You go in the loop, and when it arrives here again, then it's stopped, right? Because there is no recognizer for G. So you need this thing to make sure that every message goes at most once in a loop, okay? Good. All right, so this coded channel can help us mix and match any set of inputs on any set of outputs. So from now on, we'll assume that we have this box where you can route anything to anything, okay? Of course, all the caveats still apply. So when you send an input, you have to wait for it to completely dissipate before sending the next one, and so on, okay? So let me finish here, and then we'll really go to the final proof next time by showing what is our computing element, okay? And so the computing element will be a finite automaton, okay? And what is a finite state automaton, okay? So it is very simple, okay? It's some machine that, as the name implies, has a finite set of states. So in this case, the states are represented by these circles. So this is a turntable, okay? It can be locked or unlocked. And then it has also a finite set of possible inputs. And these inputs can produce some transitions between states, okay? This is the traditional definition of the finite automaton. We'll also add that it can output things according to the transition it takes, okay? So let's see, for example, this finite state automaton. It has two states, locked and unlocked. It has two possible inputs, push and coin. And it has these four possible outputs, okay? So what happens? This is the start state, denoted by this thing. So if you're locked and get pushed, you remain locked. If you get a coin when you're locked, you become unlocked, and so on and so forth. If you get a coin again, and then you can also output some messages whenever you. So this is very simple, okay? But this can allow you to compute a lot of stuff, okay? And we'll define more what it is in the next lectures. But you can see that you can make a little program with this, right? So yeah, finite number of inputs, finite number of states. You have a transition function that takes as input the input and the current state and decide what is the new state. That's it, okay? So how do we implement this in the von Neumann CA automaton? And you will see it's the simplest machine that will build so far, I think. So the inputs will be simply coded sequences, okay? So each input we represent by a specific string. And we can recognize the input with the recognizers, okay? The outputs, they are also coded sequences, which we create by pulsars. And then the current state, the current state is simply a periodic pulsar, or if you want, a flip-flop gate, okay? When the flip-flop gate is on, it means that this specific state is the state we are in. So if you have 5 flip-flop gates, you have 5 possible states, and you make sure that only one of them can be on at the same time, okay? So how does it work? So we send an input. The input attempts to interact with all the flip-flop gates. So it goes through all the flip-flop gates. And naturally, it will only pass through the one which is on, okay? So that way you can route the input to only interact with one state. And then depending on which state it passes through, it will do some things. So it will switch its state, potentially, and output some output, okay? So this is kind of murky, but let's actually implement something specific. So we have the following state machine, okay? It has an internal state. It has 2 possible internal states, okay, D0 and D1. 2 possible input state, I0 and I1. And two possible output states, O0 and O1. Okay, very simple. And these tables tells you what happens each time you get an input. So if you're in state D0 and get I0, you will remain in D0 and output O1. Okay, super simple. So this is the coded channel that, or this is the machine in von Neumann that implements this automaton. Okay, so let's just try it with D0 and input I0. Okay, so what will happen? So if we're in state D0, it means that this periodic pulsar is on. Okay, this one is off. That's the representation we choose. And so these two strings are full of excitations, always, right? But of course, nothing goes through because you have this other arrow that does the end. So let's assume you have a I0 coming in, okay? It's recognized by this R of I0, and it's input in the coded channel A0, okay? And this coded channel is such that AI is routed to BI, okay? So let's see. The A0 receives an input. Where are some B0s? There is one here, okay? So this will get an excitation, go here, pass through, and go to A5. And the A5 is just output O1, which is what we wanted. So the output is fine. Then the A0 is also routed here at B0, but this one doesn't go through, right? Because this one is off. So nothing else happens. So we remained in state D0, and we outputted O1. So this works, okay? And I suggest that at home you try the other possibilities. So start with D0 with an input of I1, and then follow what happens, and you'll see that you get exactly what you want, okay? So we have also the finite automaton. So the computing unit is constructed in von Neumann. And all we needed was recognizers, pulsars, and periodic pulsars, okay? Of course, for the recognizers, you needed the NOT gate, but that's to be expected, right? Because we are creating a computing element. And okay, we have this. So we said we need the computing element, the tape we are missing, and we're also missing the thing that actually construct the states, okay? So I was planning to do this today, but we have no time. So next time, we will take a look at the constructing arm. So actually how to make an arm that constructs the machine that we wanted to construct inside von Neumann. And we'll see it, we will actually implement it, okay? It will not be abstract, it will actually be something that we can actually see how it works. And from that, we'll have all the pieces to show you how to construct a replicator. And yeah, and the interesting thing that we'll see is that there is some people that actually constructed an actual replicator, like the actual machine with all the states. And I found it on the internet. We put it in our program. It was not working. So I sent an email to the guy who actually constructed the state, and he answered. So it's William Buckley. And so now I'm working with him to fix it. So hopefully it will be fixed by next time so we can actually see it working. But yeah, so next time we'll do this, and we'll probably start on the Turing machine theory stuff. Yeah. Okay.